Alright, hello everyone. Welcome to my medical statistics class. I'm King from the School of Public Health Department Statistics. Today we will learn Chapter 6. The title for Chapter 6 is Two Samples Statistical Inference. We will still talk about something about statistical inference. And we have mentioned that inference means we can use the data or the informations which we get from the samples to infer the results of the populations. This method usually can be used for the comparison of different populations. In Chapter 5, we have learned some methods used for one sample statistical inference. So, at first, let's review what we have learned in Chapter 5. In Chapter 5, the methods of statistical inference were based on one sample. So, do you remember what's the meaning of one sample? And how do you know how many samples are there in a question? Yes. So, one sample means there must be only one sample in the question. So how can we know that? We can identify the numbers of samples by using the number of sample size. We often use the little n to represent sample size. So, if you can find only one number of n, that means there is only one sample in the question. So, in Chapter 5, we have learned something about one sample test. So that means there is only one sample in the question. There is not another one. And in statistical inference, we have two methods. The first one is estimation. And the second one is hypothesis test. We have these two methods in statistical inference. And in Chapter 5, all the methods we have learned is based on one sample. And in one sample estimation, when we want to calculate the confidence interval for the population mean, we have two methods, and either of the two methods is based on a special distribution. One is based on Z distribution, and another one is based on T distribution. So it's similar in one sample hypothesis test. We have two methods. The first one is still based on Z distribution, and the second one is based on T distribution. And here, let's clean it. in estimation. Most often, we calculate the 95% confidence interval. 95 CI, that means 95% confidence interval. And we said that the confidence interval is consisted with two numbers. The first one is the lower bound, and the second one is the upper bound. So the confidence interval is actually a range between these two boundaries. And we said that for the population mean, namely mu, it has a probability of 95% to locate in this range of confidence interval. So that means mu is more than the lower bound and less than the upper bound. And its probability for mu is more than lower bound and less than upper bound. The probability should be 95%. So we have, for the one sample test, we have two methods to calculate the 95% confidence interval. The first one, we can use Z distribution. So, do you remember the formula? That formula is very important. Mu is more than x bar minus Z half alpha times sigma over square root n, and less than x bar plus Z half alpha times sigma over square root n. This is the first method for 95% confidence interval. It's based on Z distribution. And in the second method, which is based on T distribution, it has a different formula, but the formula is very similar with the former one. That is x bar minus T times S over square root n. Mu is more than this number and less than another one, x bar plus T times S over square root n. So we can find that based on different distributions, the formula is different. So how can we know when can we use the former formula and when can we use the later one? That is the precondition for the formula. We have mentioned that if we want to use the Z distribution, the precondition should be sigma is given. So when sigma is given, we can use Z formula. But if sigma is not given, we don't know the sigma, or we don't know the variance. Variance is sigma square. So if sigma or sigma square is not given, we cannot use the first method. At this time, we need the second formula. So the precondition for T is sigma is not given. So that is the difference between Z and T confidence interval estimation. And the next one, how about the hypothesis test? we said that hypothesis tests have the same procedure for almost all of the methods. That is, step 1 establish two statements of hypothesis and set a number of alpha. Alpha is significance level. Usually alpha equals to 0.05. And step 2 is to calculate the test statistic. For example, in z-test, we need to calculate z value. In t-test, we need to figure out the t value. And step 3 is to make decisions. Reject H0 or not reject H0. So how can we know when to reject or when to not reject? We need to find the probability for the test statistic, which we calculated in step 2. At this time, we need the help of appendix tables. So for the z-test, we need to use table A1, the z-table. But if we use the t-test, we need table A2, the t-value table. And we need to find a special standard t or z value. We can get this value from the appendix table. For z, when alpha equals to 0.05, z is 1.96. So I think Teacher Gao have told you that you need to remember this number. Z equals to 1.96. That is, when alpha equals to 0.05 is corresponding z value. The standard z value is 1.96. And t, how can we get the number of t? You don't need to remember any number of the t value in the table A2. I have mentioned that last class. But you should notice that you need to remember how can we get the standard t value from the table A2. You need two numbers to identify the standard t value. The first one is alpha. And we said that in t value, alpha actually means two-sided alpha. So that means two-sided alpha equals to 0.05. Because in step 1 of the procedure of hypothesis test, we set alpha as the number 0.05. So this is the first number you need. And the second number is nu, or we can call it degree of freedom, df. And nu equals to the sample size, little n minus 1. So with the help of these two numbers, you can get the standard t from table A2. And then you need to compare the t value which we calculated in step 2 with the standard t or z value which we get from the table. Sorry, it's t or z here. We need to compare the test statistic, the t or z value, with the standard value we get from the table. And the result of the comparison is the same. If the number you calculate is bigger than what you get from the table, that means p is less than alpha. So we need to reject H0. When H0 is rejected, that means the two populations are different. But if we find that, I will change another color. If we find that t, what we calculated, is less than the standard t or z, that means the test statistic which you calculated in step 2 is less than what you get from the table. That means p is bigger than alpha, so we cannot reject H0. So if we cannot reject H0, that means the two populations, they are the same. There is no significant difference between the two groups, between the two populations. So that is the procedure of hypothesis test. And we said that all of these above mentioned methods are used for one sample test. That means there is only one sample shown in the question. But the hypothesis test is used for comparison. We need to compare A with B. But if there is only one sample, how can we finish the comparison? Most often, in the question of one sample test, a sample will be given. That is what we call it, one sample. And the question will show us a given population. So actually, we need to compare this given population with the given sample, the given one sample. So that is one sample test. But sometimes in our research, population cannot be given. So what we can know is sample A and sample B. So there are two samples in the question. There is no any given population. So how can we do that? It's not one sample test anymore because we have two given samples without a given population. So we call it two samples statistical inference. So that means in chapter 6, we will learn some methods used for statistical inference of two samples. So that means there will be no given populations in the question. And here is my question. How many sample size will be shown in the question? Let's think about it. Do you remember that? We said that in one sample test, there is only one sample size will be shown in the question. So if this method is called as two samples statistical inference, that means in the question there must be two sample size. Yes, so you will find two sample size, two little n. One is for sample A, we call it n1, and 2 is from sample B, we can call it n2. So you can find two numbers of sample size. So if you can find two numbers of sample size, that means these two numbers represent the number of persons or individuals. That means it is a question about two samples, not one sample. Okay. Okay, so here the comparison of two sides of observations is a common problem in medical field. For example, if we have two drugs, A and B, and both of the drugs are used for reducing the blood pressure, and now we want to know which one is more effective. So we need to compare the effectiveness of drug A and drug B. But which one is the population? We have mentioned that population is so big, so large, so most of the time we can know nothing about the population. So here we can draw two samples from the two populations, that is population A and population B. We can draw a randomly sample from either population, and then we can compare these two samples and to infer its underlying populations. That's what we need. That's what we need to do in chapter 6. The comparison of two samples results is rarely asking if the underlying parameters of two different populations differ. So you can find that here is a keywords. In medical statistics, you need to identify the keywords. If you can find a special keywords, and you will know what method you can use. For example, when we are talking about the confidence interval, and you will find that in the question, in the last sentence of the question, that is the purpose of the study. You will find that the purpose of this study is to calculate the 95% confidence interval of the population mean. So this is the keywords. So this is a question about estimation, not about the hypothesis. But when we are talking about the hypothesis test, actually we mean to compare the effect of drug A and drug B. Or we can say that we want to identify if there is any difference between drug A and drug B. So different or difference, that's a very important keywords. So if you find some kinds of these keywords, you can know what methods you can use to solve this question. For example, if you can find the word of difference, then you can use hypothesis test, not estimation. So in chapter 6, the data from the two samples are assumed to follow normal distribution. So that's a very important precondition. Z-test and T-test are similar with the normal distribution. Actually, Z-test is based on normal distribution. Normal distribution is also called it as Z distribution, and T distribution is from Z distribution. So here we won't talk too much about this one. In chapter 6, we have two kinds of T-test. Please notice that there is no Z-test which is used in two samples test. So Z-test, what we have learned, is only used for one sample. Only for the one samples test. There is no two samples Z-test. So in chapter 6, we will learn two methods of t-test for two samples test. Both of the two methods are based on t distribution. There is no z distribution in two samples test. Okay, let's clean it. The first method is called the paired t-test. So you can find that t-test. So that means in step 2, you need to calculate the t value, and it has the similar formula of the calculation. So it means that after the calculation of the test statistic, you need to compare what you have calculated with the standard t value which you get from the table A2. It's none of the business with the table A1 with the z value. It's based on t-test. And we can find that here is a special word in the title, that is paired. So what's the meaning of paired? This word actually means matched. So what's the meaning of matched? So here, many biological studies are designed to produce observations in pairs. So that means we usually use two persons or two individuals as a pair. For example, to know the effect of a new drug in reducing blood pressure, the blood pressure of each individual is recorded both before and after treatment of the drug. So what's the meaning of paired? So we can find here is another keyword, before and after. So let's think about it. Now we have only one drug for reducing blood pressure, only one drug, that is drug A. And this is Tom, that is a person, Tom. And now we want to know if the drug A is useful or not. So before Tom used drug A, we measured his blood pressure, and we find that its blood pressure, for example, 121. And after that, we let Tom use the medicine. And after he used the medicine, we measure it again. And we found that his blood pressure is 104, for example, 104. And here we can find that we have two numbers, 121 and 104. And we can find that these two numbers are in pairs. And the two numbers have a special relationship. We can find that this number comes from the person Tom, and the second number is from the same person, right? So before and after the two methods, the two numbers are from the same person or the same individual. We said that these two numbers are matched. These two numbers are matched because they come from the same person. Okay. So here is another person. That is, for example, John. And we measure his blood pressure before 141, and after he used the medicine, we measure it again. That is 126, and we find that these two numbers are from the same person too, but not Tom, right? Both of these two numbers are from John. So these two numbers are matched, just the same with the first two numbers. And we have the third person, for example, Jack. And we have so many persons. For each person, we can measure two numbers, before and after, and we can find that the two numbers from the same person are in pairs, or we can say they are matched. And all the numbers of before is considered as sample 1, and all the numbers from after are considered as sample 2. At this time, we say that sample 1 and sample 2, they are matched. So that is the paired samples. These two samples are paired samples. So that is the meaning of paired. But please notice that the keywords for paired samples, before and after, can be considered as the keywords for paired samples. But there are still some other keywords. For example, matched. That is another keyword. For example, let's think about it. In the last example, we use before and after, that is matched, or we can say that is paired samples. And here we have another example. Now we have two methods, drug A and drug B. And we find two persons. For example, the twins. And we want the older one use drug A, and the younger one use drug B. And we will find that because they are the twins, so the results of the older and the younger, actually they have some special relationship. They have the same, maybe they have something the same in genetics, right? They have the same gene, DNA, right? Okay, so let's take another example, not the twins. For example, we have two persons, 1 and 2, number 1 and number 2. These two patients, they have the same age and gender. For example, both of these two patients are 50 years old and they are male. So we find that two numbers, A and B, these two numbers have a special relationship because these two numbers have the same age and the same gender. And we can say that these two numbers, or these two patients, are matched in age and gender. So we also call it matched samples or paired samples. So here we can find that matched is another keyword for paired sample. Okay, so that is the meaning of paired. So two samples are said to be paired when each data point of the first sample is matched to a unique data point of the second sample. We have explained what's the meaning of that. Matched pairs design has the advantage of controlling many extraneous sources variation in data. Actually, in study design, we often call it this paired sample or this matched sample as matched pair design. Matched pair design. So that is how can we design the study? How can we group all the patients? We just make some parts of the patients go into the group 1 and the others go into the group 2. That is design. So how can we do that? If you use the matched method or the paired method, we call it matched design or matched pairs design. So for this kind of study design, we need to use paired test. And why do we need this type of design? The advantage is this method can control some variation in the data. For example, we compare drug A and drug B, still this example. But we find that most of the patients in sample A is male. But in sample B, all of the patients are female. And we find that the number of sample A is 100 and the number of sample B is 200. Does that mean the drug A is useful than B? Do you believe that? No, we don't believe that, right? Because we can find that the patients in the two samples are different. This one male, this one female. The gender is different. And the effectiveness of the drugs can be influenced by the gender. So how can we reduce the influence of the gender? One way is let both of the groups have the same gender. So paired design is a good way or a good method to reduce the influence of the gender. So if the number 1 patient in sample A is a male, we need a male which is in the sample B. If the second patient in sample A is a female, we need a female too in sample B. So when we compare these two samples, each pair of the patients have the same gender. So when we compare these two numbers, the gender, because of the same gender's influence is reduced. So finally, we can find out if A is better than B or not. So that is the advantage of matched pairs design. Okay, so now we know what's the meaning of paired. what's the meaning of paired design? And how can we do the calculation? How can we solve the questions of paired design in medical statistics? Now let's read this example. This is the two-sample paired t-test for the mean of normal distribution. And we notice that this is a question about two samples and the two paired samples. And in two paired samples, we need to use t-test because we have mentioned that there is no z-test in two samples test. So we can only use t-test. So we call it the paired t-test. Just similar with in chapter 5, we call it one sample t-test. In chapter 6, the first method is paired t-test or paired sample t-test. Okay, let's read this question. A certain drug is to be tested for its effect on blood pressure. 10 women patients have their diastolic blood pressure measured before and after receiving the drug, with the results shown below. Here we notice that we find the keywords, right? Before and after. So that means it must be paired, right? The paired sample. So we can use paired t-test. Okay, so the last sentence. Does the drug significantly reduce the blood pressure at the 0.05 level of significance? So we can find that here there is no keywords of difference, right? But we notice that it mentioned significantly reduce. So reduce or not? How can we know if that is reduced? We need to compare, right? Compare before and after. If the numbers of after is lower than before, that means reduce. If after is higher than before, it means increase, right? If before equals to after, that means there is no difference, right? So here, significantly reduce is similar with different. That is a keywords. So we can know that we need to use hypothesis, not estimation. We don't need to calculate the 95% confidence interval. We just do the hypothesis test, right? Okay, so here, the following is the number of the research. We can find that this is the first column. This is the patient, the number of the patient. We have 10 patients from number 1 to number 10. For each patient, we have two numbers, and these two numbers in pairs are matched. The first one is from before using the medicine, and the second one is after using the medicine. So we call it paired sample. So it's paired t-test, right? Okay, so the last thing is the procedure of the hypothesis test of paired t-test. So it follows the same procedure. That is step 1, step 2, step 3, and finally the conclusion, right? Here, the only thing you need to notice that is how to calculate the test statistic. The test statistic is still t-value, but the formula is different, a little different from what we have learned before. So let's think about it first. Now we want to know if the drug can change the blood pressure or not. So when one can say that the drug can change the blood pressure. When can we say that? Yes, when after is lower than before or after is higher than before. That means the drug is useful because the blood pressure is changed, right? Okay, so that means let's think about it. If we suppose the drug is not useful, the drug is not effect, then the difference of before and after should be equal to 0. Is that right? If the drug is not useful, that means that drug cannot change the blood pressure. So that means before and after they must be the same. So the difference should be 0, right? Yes, but we have mentioned that in medical statistics, we have error, especially random error. So that means if the difference is really 0, there is no difference, there is no effect of the medicine. But when you measure the blood pressure for a person for 2 times, you will find that the number may be different. Why? What can cause this difference? What can cause this difference between the measured numbers? That is random error. So if the population mean of the difference of before and after is 0, we can believe that the drug has no effectiveness. Not with the data of the sample, but the population. We said that if the mean of the population of the difference is 0, then we can believe that the drug is not useful. So here we need to calculate the difference of before and after. For example, here we use d, the little d, to represent the difference. And you can use before minus after. And you can also use after minus before. For example, here I use the little one, after minus before, and we get the difference. So at this time, we will find that in these 10 pairs of numbers, we can get 10 difference value, right? But we find that some difference values are positive and some ones are negative, right? Positive means after is higher than before, and minus means after is lower than before. And if the distribution of the difference is symmetric about 0, that means maybe half of the difference is positive and half of that is negative. It's symmetric about 0. And we will find that actually the medicine is not useful. But if all of the difference or most of the difference, almost all of the difference is positive, that means after is higher than before. Or another one, if the difference, almost all of the difference or all of the difference are negative, that means after is lower than before. And we can believe that the drug can change the blood pressure. So here, the only thing we need to do is to test whether the difference is symmetric about 0. So actually, we need to test the population mean of the difference equals to 0 or not. Okay, let's take a break.